All right, so here in this particular glancing collision problem, you're given an initial puck A is moving to the right, puck B is initially at rest, and then after the collide, puck A is going to go in the northeast direction, while puck B goes in the southeast direction. And it wants you to find the final speed of block or puck B, and then the two angles alpha and beta, respectively, to the horizontal axis. All right, so let's do this one. The first thing I want to find for this one is actually the speed at the end, only because it says elastic. I already know the energy, kinetic energy coming in. I also know the kinetic energy of puck A afterwards. So therefore, the only thing missing is the energy of puck B, which allows me to set up conservation of kinetic energy. Because it's elastic, KEI must equal to KEF. So I'm going to start with the statement. The initial kinetic energy of the system must equal to the final kinetic energy of the system. So even though they ricochet off in two different directions, the sum of the energy must equal. So I'm just going to go ahead and set this up. I'm going to go ahead and 1/2 MA VAI square plus 1/2 MB VBI square. And that's going to equal on the right side to 1/2 MA VAF or VFA square plus 1/2 MB VBF square. However, I can just go ahead and cross some stuff out. I'm going to cross the 1/2 in all these terms out because it's kind of redundant to multiply everything by half. And I'm also at the same time going to cross the kinetic energy of puck B initially out because it wasn't moving, okay? Because it wasn't moving initially, it doesn't have any kinetic energy. All right, so I'm just going to go ahead and do that. Just clean up a little bit. Now, on the bottom, MA is given as 0.5 kilograms in the problem. It had an initial speed of 4 to the right. I'm going to square that. And likewise on the right side, MA once again is 0.5. The final speed of puck A is given as 2 in the diagram here. Again, it's given here as 2. The problem calls it VA2. I'm just going to call it VFA. I like initial and final. So we're going to square that and then plus the kinetic energy of puck B here, or just MBVBF, which is given as 0.3 kilogram, and then VBF square is what I don't know. So that's kind of my only missing term here. So I'm just going to go ahead and clean this up a little bit. On the left side, we can do this. 4 squared is 16. 16 times a half is 8. And then over here, 2 squared is 4. 4 times a half is 2. And then the term with the VBF square remains the same. So I'm going to go ahead and keep it as is. And here I'm just going to come out like term. There's an 8, there's a 2. I want to subtract 2 on both sides. So really I'm just going to get 6 on the left side. And that equals to 0.3 VBF square at this time. In order to get VBF squared by itself, let's go ahead and do algebra correctly. Divide both sides by 0.3 first. And then once you have this, you can then take the square root in order to get VBF by itself. So 6 divided by 0.3 is 20, and then that'd be the square root of 20. And you can simplify that and leave it as 2 radical 5, or if you want, you can go ahead and simplify that. That would be 4.47. Okay, so that is the speed of puck B after the collision. Okay, so that's the answer or the first part of this particular question. Now let's go ahead and find alpha and beta, and this particular next segment, it's the challenging part, I think, of this problem. Okay, so here I've carried over the diagram. So in order to find alpha and beta, now you need to use conservation of linear momentum. Okay, so I'm going to go ahead and just start with the x direction. So here I've made a statement that the initial momentum of the system in the x direction must equal to the initial momentum of the system in the x direction as well. So I'm just going to go ahead and break it up. Here initially we have a puck A moving to the right. We also have a puck B at rest, and then afterwards both pucks are moving to the right. It's just one is moving to the right and up, the other one is moving to the right and down. Okay, so on the right side here I have MA times VFAX, and likewise MBVFBX. I want to emphasize the subscript X here because you do need to focus on breaking these velocity vectors into components. All right, I'm going to go ahead and cross out MBVBIX because it was initially at rest. An object that's at rest has no momentum. And then from here, I'm just going to go ahead and show you how to find VFAX and VFBX, just in case you're needing a little guidance with geometry. So here in the diagram, the VFA is a diagonal vector pointing up and to the right in the northeast. So therefore, VFAX is this dashed component. So alpha here touches the horizontal axis, so nothing fancy. The leg that touches the angle horizontally here, that's going to be your cosine. Okay, so when you do geometry, if the angle given touches the horizontal axis, your adjacent is your cosine. So in this case, this is why VFAX is 2. Well, 2 is because the hypotenuse is 2, and it's cosine of alpha because this is the adjacent. Okay. Other than that, same thing here with the VBFX. VBFX is going to point to the right as well, and likewise, beta also touches the horizontal axis. So VFBX or VBFX, whatever you want to call it, is going to be 4.47. Keep in mind we got this answer previously in part A, or in the previous slide. The speed of puck B afterwards, which is this vector here, the hypotenuse, is 4.47, and this is your adjacent leg, which is the horizontal component. That would be cosine of beta. Okay. All right, other than that, I'm just going to go ahead and plug it in. MA is given as 0.5, VAIX is 4 in the diagram, MA is 0.5, VFAX is 2 cosine of alpha, and then MB is 0.3, and then VBFX can be broken down into 4.47 B or cosine of beta, and that's where these components come in super handy. Okay, now I'm just going to clean it up a little more. 0.5 times 4, 0.5 times 4 is 2. And then here I'm just going to simplify. 0.5 times 2 is just 1. And then 0.3 times 4.47 on your calculator should give you about 1.341. And then the cosine of beta. As you can see here, in this particular point, you have a one statement with 2 unknowns, right? You have alpha, which is an unknown, and then you have beta, which is also unknown. So it's impossible to solve unless you set up another physics statement, right? So let's go ahead and do that. Here, I'm just going to go ahead and isolate for cosine of alpha, just because cosine alpha is already by itself. It's standing on its own. There's no coefficient. So I'm just going to go ahead and subtract both sides by 1.341 cosine of beta. So this positive term, I'm going to move to the left side, which makes it negative. And now, again, I'm still stuck because I have 2 unknowns, right? I'm going to go ahead and set up information in the y direction. So likewise, net momentum in the y direction initially must equal to the final momentum in the y direction afterwards. All right. Well, the system was initially moving to the right, and puck B was at rest. So initially, there is no momentum in the y direction, which suggests that you also need to get 0 back on the right side. Well, if you look at this particular diagram correctly, you have a puck that's moving upward, and then you have a puck that's moving downward. Those 2 components must equal. Okay. Why? Because you have to get back 0. So I can say that PFAY must equal to PFBY. Now, let's go ahead and do that. Likewise, earlier, if you kept up with the geometry for the horizontal component, I'm just going to do the same here with the vertical component. I can see that VFAY is just the hypotenuse, which is 2 times sine of that angle. It's sine because it's opposite. And then likewise on the bottom, however, you notice that this particular component is pointing downward, so it's important that you pay attention to directions, okay? Here, VBFY is going to be 4.47 times sine of beta, because the angle down here is beta. Now that I have that, I'm just going to go ahead and substitute this in. VFAY, I can break it up into mass times velocity in that direction. So the mass here for A is 0.5, and then VFAY is 2 times sine of alpha, and that's why this is done for you. And then I'm going to subtract it. Notice I highlight though in this particular part, the momentum of the second puck is moving to the right and downward. So it's important that you introduce a negative sign, otherwise you can goof on algebra stuff. All right. So I'm going to go ahead and break up PFBY into mass times VFBY, mass being 0.3, and then VFBY over here that I'm circling back and forth here that I did is 4.47 times sine of beta, and that's where that term is from. As you can see from here, you have 2 unknowns. You have alpha and beta as well, just like the previous setup. In the x direction, you have 2 unknown, alpha and beta. So I'm just going to go ahead and clean this up. 0.5 times 2 is 1. So here I have sine of alpha by itself. And then this 0.3 times 4.47 is going to be, once again, 1.341. And here I'm just going to go ahead and isolate for a sine of alpha by moving this negative 1.341 sine beta to the left side and changes the sign. So it's negative here. So when you move to the other side of the equal sign, it just changes sign. Okay. So as you can see here, you have really 2 unknowns. You have 2 systems of equation, right? You have a cosine of alpha. You have a sine of alpha by themselves. What do you do with this? And I think this is the difficult part of this particular problem. Well, you have to recognize that you need to use this trig identity, right? Sine square of theta or sine square of alpha, whatever the angle is, plus cosine square of that same angle must equal to 1, okay? So here I made a note for you. This is your trig identity. Well, I don't have sine square and I don't have cosine square. What I do have though is cosine by itself and I have sine by itself. So what I can do is I can just square them and then I can just substitute them for the statement. So I'm just gonna go ahead and do this to the top one first. See here on the top, using the information in the x direction, I have cosine alpha square. However, I want to square both sides, okay? So I'm not going to show you how to do FOIL because that's just algebra stuff. So if you need to take a minute, practice how to FOIL. But I made a note here, you have to FOIL. So you have to FOIL this side. So if you FOIL the left side correctly, you get 4 minus 5.364 cosine of beta plus 1.79 cosine square of beta. Okay, so again, if you don't know how to FOIL, I would suggest you pause and FOIL just so you can master that skill. All right, so now that I have cosine square, well, here I have this term already, but now I need sine square. But here in my work for the y direction, I have sine alpha by itself. So what I'm going to do is I'm just going to square that. This term is easy to square just because you're not adding anything, so you don't have to FOIL here, right? You're just multiplying. So here, I'm going to square the right side, which makes it sine square alpha, and then I want to square the left side. 1.341 square is 1.798, and then sine beta square is also that right there. All right, so now that I have cosine square and sine square of the same angle, I can substitute in for here. So I'm just going to do that really quick. So here, sine square is substituted out for 1.798 sine square beta, and then cosine square of alpha is all this stuff up here in blue. So I carry the left side down, where there's the 4, there's the negative 5.364 cosine of beta, and then plus the 1.798 cosine square of beta. And all that equals to 1. But here's the trick, here, well, I wouldn't say a trick, here's the visual thing that you have to observe. Here you have sine square of beta, here you have cosine square of beta, right? So therefore you can combine these two terms. So what I do was I just factor out the 1.798, right? Because they involve the same angle. So here I factor it out. So here I have in parentheses sine square of beta plus cosine square of beta plus 3. Now in case you're like, wait, where's the plus 3 from? Well, this is a positive 1 on the right side. I want to move it to the left side. So 4 minus 1 is 3. That's where the 3 is from. Well, on the right side here, all of a sudden you have this 5.364 cosine of beta. Well, that's because this term right here, cosine of beta, right? This is cosine of beta. It's not cosine square beta. Here's this negative term, so I want to move to the right side of the equal sign. So that's why it's positive. So I kind of did a couple of algebra step in one. So if you need to, work it out for yourself so you can keep up. So here I'm just going to clean it up. Well, I know that sine squared beta plus cosine squared beta is just equal to 1. Well, here we just have 1.798 times 1, which is itself plus 3. So I'm just going to clean that up a little more. So the left side literally is just 4.798. And then from here, in order to solve for a beta, you have to divide both sides by 5.364 first. And then you notice here you have cosine beta on the right. So to get beta, you just do cosine to the negative 1 on your calculator. And that would be 4.798 divided by 5.364. And then that should yield an answer of 26.56 degrees. So that's beta for you. Okay. But now that you have beta, you need to find alpha, right? So, well, to find alpha, I think the easiest way is just to use this function that's just gotten large on the screen here. Here you have the statement, right? To find alpha, you need beta. Well, we already found beta, so I'm just going to carry the statement down. So 1.341 sine beta is equal to sine alpha. I know beta, so I'm just going to substitute in. So beta here is just 26.56 degrees. Nothing fancy. So if you punch all the stuff on your left side, or all the stuff on the left side on your calculator, you should get about 0.5996 sine of alpha. And similar to finding beta, to find alpha, here's sine. So you need to do sine to negative 1 in order to get alpha by itself. And then that's it. So if you punch this in on your calculator, sine to negative 1 of 0.5996, and you'll get an angle of about 36.84. Okay, so that's that for this problem. I hope you understand the second side. I think, which again, is the hard part about this problem. If you need to, watch it again. All right, stay nerdy, don't be white.